Introduction to differentiation. This is the line y is equal to 2x. The gradient of the line is equal to 2. The gradient is 2 everywhere on the line. This is the graph of y is equal to x squared. Now the gradient at any point on this curve changes. So for example, the gradient right here is quite flat in this region of the graph. Looks as though it's 0. And then the graph starts to get steeper, and the steepness of the graph is represented by its gradient. So the gradient's increasing as we move along here, and also if we look at this side here, the graph's getting steeper as we move in this direction. The gradient's negative on this side, and it's 0 here in the center, and then it starts to increase here again, it's positive, and so on. In mathematics, to work out the gradient of a curve at any particular point, we're using something called differentiation. It's a technique used to work out gradients of curves. If the equation of a curve, so equation of curve is y is equal to x to the power of n, to work out the gradient any on this curve, we use the function n times x to the power of n minus 1. This is called the gradient function, and the notation that's used is this: dy by dx is equal to this. Dy by dx is just saying a change in y divided by a change in x. It's just a fraction. But that's the notation that you use to represent the gradient function. That looks complicated. It's not. It's quite simple. So for instance, let's say we have a curve which has the equation y is equal to x to the power of 3. To work out the gradient anywhere on this cubic curve, we use dy by dx is equal to, and just following this formula, the power n comes to the front, so the 3 comes to the front, and then you've got x to the power of n minus 1. Well, n is 3, so 3 minus 1 is 2. So for any particular point on the curve, if we substitute a value of x, so if we put the x coordinate into this formula, we can work out the gradient on the curve. So for instance, I could say point A is on the curve, and point A has coordinates 2, so the x coordinate for point A is 2, so the y coordinate on the curve, equation of the curve, 2 cubed, which is 8. That's the y coordinate. So I know this point is on the curve somewhere. What's the gradient of the curve at point A? Well, we use the gradient function. I mean, this thing is specifically called the derivative. Okay, so using this derivative, I can say that at x is equal to 2, dy by dx, the gradient of the curve, is equal to 3x squared, so 3 times x, which is 2, squared. And as you can see, this derivative is based on a value of x, which is why I'm putting an x value into this. So 2 squared is 4 times 3 is 12. So 12 is the gradient of the curve at this point. Okay, so here is the curve that we were just looking at. Y is equal to x cubed. That's the equation of the curve. When x is equal to 2, y is equal to 8. So this point here is our point A with the coordinates 2, 8. And the gradient of the curve at this particular point is equal to 12. That's what we've worked out from using differentiation. As soon as you move away from point A, so if I come down this way here, or go this way here, the gradient will change. It's 12 right there. Okay, so let's have a look at all this again. You always start off with the equation of a curve, and then you differentiate that to get its derivative. And the derivative is just the gradient function. These are the same thing. And this is the notation that we have to use when we write down the derivative, that dy by dx is equal to something. And this is a standard formula that you need to memorize. So let's have a look at a few more examples using this formula for differentiation. So let's say we have y is equal to x to the power of 5. Okay, so dy by dx, so the gradient function, or the derivative, is equal to, so the power comes to the front, times x to the power of, and then you reduce the power by 1. It was 5, and now it's 4. What would happen if we started with y is equal to 2 times x to the power of 5? Now this bit is still the same, but we have to multiply by the 2. So I need to do this. So then the derivative, or the gradient function, will be 10x to the power of 4. The easy way to do this is this. Power times what's in front, so 5 times 2 is 10, and then take away 1 from the power, like this. So y is equal to minus 3x to the power of 3. So dy by dx, the derivative, is equal to this 3 here times this minus 3 that's in front to give minus 9 times x to the power of, and subtracting 1 from the power there, 2. Y is equal to x cubed plus x squared. So if you have multiple terms, dy by dx is equal to, okay, so differentiate the first term, 3x squared, plus differentiate the second term, 2x, and when you subtract 1 from the power, it's the power of 1, but you wouldn't write the power of 1, we just leave it out, so this is what you get. Y is equal to 3x. Well, that's just a straight line, it's not a curve, and we can tell the gradient is 3. It's in the form y is equal to mx plus c. M is the gradient, is 3. But we can still use differentiation on this as well, if we want to. There's no point, but we can. So that's 3x to the power of 1 at the moment. So the 1 multiplies with the 3 to give us 3, and then you've got x. You subtract 1 from the power, so 1 minus 1 is 0. Well, anything to the power of 0 is always 1. So that's 1 times 3, which is 3. So we've just worked out the absolute obvious, that for a straight line, that's the gradient. Okay, now I'm going to modify the equation of this line slightly. So let's say if we had y is equal to 3x plus 2. So y equals mx plus c. So that's the y-intercept for this line, and that's the gradient. We know that dy by dx will give you the gradient function. The gradient of this line is still 3. It's got nothing to do with the y-intercept. Now you can put any number you like there. For example, I don't know, 12. It's still got a gradient of 3. So on this side here, when you differentiating the 3x term will still give you what we had before, which was 3, x to the power of, that was to the power of 1, so you subtract 1 to get 0 here. Differentiating a constant always gives 0. So there's the plus, and that 12 there just gives you 0. And if you simplify this, x to the power of 0 is 1, times 3 is 3, add nothing is still 3. So if you had this, y is equal to x squared plus 8, and you differentiate, so dy by dx is equal to, so from the x squared term, we've got 2x to the power of 1. Constants give you nothing, so that's it. Differentiating y is equal to the square root of x. I need to write this in index form first. So this is the same as y is equal to x to the power of a half. Okay, so using the same rule as before, dy by dx is equal to, bring the power to the front, so we've got a half, x to the power of, and then subtract 1 from the power. So what do you get if you've got a half minus 1? A half minus 1 will give you minus a half. So the power here is minus a half. Differentiating y is equal to 1 over x squared. I need to rewrite this as y is equal to x to the power of, that's a positive power there, this will be negative then, x to the power of minus 2, these are the same. And now I can differentiate, so dy by dx is equal to, bring the power to the front, x to the power of, and then subtract 1 from the power, so minus 2 minus 1 gives you minus 3. So that's the gradient function for that curve there. If I want to, and I don't have to, I could rewrite this. X to the power of minus 3 is the same as 1 over x to the power of plus 3. Opposite signs. That's a minus, that's a plus. I was multiplying this by minus 2, so if I multiply a fraction with the whole number, that whole number multiplies with the numerator here. So you can write the whole thing like this. The wrong thing to do with this example is to do this. So from the 1 over x squared to think, well, that will just give dy by dx is equal to 1 over, and then you differentiate the x squared to give 2x. It's completely wrong. You can't do that. Differentiating something that has brackets in there, well, you have to multiply the brackets out first. So y is equal to, that's x cubed, multiplying those two gives you x squared, and now you can very easily differentiate this. Dy by dx is equal to, first term gives you 3x squared, plus second term gives you 2x. So remember, if you have brackets, multiply the brackets out first. Using function notation with differentiation. Let's say if I have a curve with the equation y is equal to x cubed. I can write something similar to this by saying that my function f, so f of x, is equal to x cubed. If I differentiate using this notation, y is equal to something, then I have a derivative that says dy by dx is equal to 3x squared. If on the other hand I've started off with function notation and I'm using the function f here, then when I differentiate here I do not get dy by dx. What you get is f dash x is equal to 3x squared. That's not f to the power of 1, it's f dash x is equal to 3x squared. It represents the derivative of your original function. And as you can see, your differentiation is exactly the same. That hasn't changed. So if I said what's the gradient of the curve when x is equal to 2, then using the y is equal to something in terms of x notation here, I'm going to say dy by dx is equal to 3 times 2 squared. 2 squared is 4 times 3, which is 12. Doing the same thing here, it's neater because all you say is this, f dash, so that's the gradient function, the derivative, when x is equal to 2 is equal to 3 times 2 squared, which equals 12. Likewise, if I said what's the y coordinate when x is equal to 2, so then you say that y is equal to 2 cubed, which is 8. Using the function notation, you just say f of 2 is equal to, so I'm putting 2 in here, that value there goes into x, 2 cubed, which is 8. And as you can see, these are very similar, but get the notation correct. If the question gives you y is equal to something, stick to that notation throughout. If it gives you function notation, then stick to that notation throughout. This equation of a curve here is y is equal to something in terms of x. You've got some x terms on the right hand side. So it was dy, this here, this letter here, dy by dx, and the x is coming from this side, equals 3x squared. I'm going to change the letters now. So let's say if it was t is equal to r cubed, and you were going to differentiate this. Now you wouldn't write dy by dx underneath, there's no y and x in here. But it's very similar, it's dt, this letter here, by dr is equal to, bring the power to the front as before, reduce that power by 1, and there you go. And as you can see, these are very similar. But you don't have to stick to x and y, you could have other letters. So here x and y are variables, here r and t are variables. In this example, f of x is equal to x to the power of 4, where on this curve will the gradient be equal to 32. So I need the gradient function because the gradient is 32. So I need to differentiate this. So f dash x, using this notation, differentiating 4 x to the power of 3. The gradient is equal to 32. So this gradient function, the derivative here, is equal to 32. So 4x cubed, our derivative, equals 32. We need to solve this equation. So dividing by 4x cubed is equal to 8 cube root x is equal to 2. So I've got the x value. I need the y value now. So on the curve, when x is equal to 2, y is equal to, so I need the equation of the actual curve now. The equation of the curve is f of x equals x to the power of 4. So when x equals 2, the y coordinate 2, because x is 2, 2 to the power of 4, that gives 16. So I've got the x coordinate and the y coordinate now for the point on the curve where the gradient is equal to 32. So at 2, 16, so at this point on the curve, the gradient is equal to 32. Now what you need to understand from this is when you're dealing with a gradient, use the derivative, f dash x. When you're trying to work out the y coordinate for any point on the curve, then use the original equation of the curve.